Hello, my name is Vidisha and welcome to our channel Coding with JS. We will learn how the JavaScript engine parses and runs our code using JIT compilation.
Your JavaScript file is just text sitting on a disk. Something has to turn that text into work a processor can do. That something is called a JavaScript engine. Most people never look inside one. But understanding it explains why some code is fast and some is slow. So today we follow one function all the way through. The journey has 5 stages. It begins with your source code. At this point it is nothing but characters. The engine cannot do anything with characters directly. It has to work out what those characters mean. That is the parser's job. The parser reads left to right and splits the text into tokens. A token is one meaningful unit, like a keyword or a name. It is roughly what a word is in a sentence. If the tokens do not form valid JavaScript, you get a syntax error. That is the earliest possible moment an error can appear. Nothing has run yet at this stage. The parser also has to decide what each token means in context. A curly brace can open a block or start an object literal. Working that out correctly is genuinely hard engineering. Here is the function we are going to follow. It takes 2 parameters and adds them. Nothing complicated, which is exactly what we want. The parser sees the keyword function and knows what follows. It sees a name, then parameters, then a body. And it records the shape of all of it. Those tokens then become a tree. This tree is called an abstract syntax tree. Each node describes one piece of meaning. A function declaration node holding a return statement node, which itself holds an addition of 2 names. The tree is what the engine actually reasons about. Every linter and bundler you use works on this same tree. When your editor renames a variable safely, it is reading this tree. When a bundler removes unused code, it is walking these nodes. So the tree is not an internal detail you can ignore forever. Now the engine has a choice to make. It could compile everything to machine code right now. That would produce very fast code. But compiling takes real time and the page would sit blank. Or it could interpret the tree step by step instead. That starts instantly, but every step costs more. Neither answer is right on its own. So modern engines do the interpreting first. The tree is turned into bytecode, a compact instruction list. Bytecode is not machine code, but it is close and quick to run. The interpreter starts executing it immediately. This is why a web page appears the moment it loads. Nothing is waiting on a compiler to finish. For most code on most pages, the interpreter is entirely enough. A click handler that runs twice does not need machine code. Now watch what happens when code runs a lot. We call that same tiny function in a loop. 100,000 times in a row. Each call adds 2 numbers and returns. And the loop closes. The engine is counting all of this in the background. A function called that often is described as hot. And hot code is worth spending compile time on. So the engine hands it to the optimizing compiler. That compiler is the just-in-time compiler, or JIT. It produces real machine code for that one function. From then on, the fast version runs instead. You can actually watch this happen. Node has a flag that reports optimization decisions. The engine marks our function for recompilation. And then optimizes it because it has become hot. That is not a metaphor, the engine literally says it. So the full strategy is simple. Interpret absolutely everything so it starts fast. Compile only the small part that runs constantly. You get an instant start and fast steady-state speed. That is the whole trick, and it is a very good one. There is one condition attached to the fast path. The compiler makes assumptions about your types. If it always sees numbers, it compiles a number addition. That version is enormously faster than a general one. But if you suddenly pass a string, the assumption breaks. The engine throws the compiled version away and starts over. That is called de-optimization, and it is genuinely expensive. Which gives you one practical performance rule. Keep the types flowing through a function consistent. Do not pass numbers sometimes and strings other times. The engine will reward you for being predictable. That single habit matters more than most micro-optimizations. Finally, there is more than one engine doing all this. Chrome and Node both use V8 built by Google. Firefox uses SpiderMonkey, the oldest of the three. Safari and Bun use JavaScriptCore from Apple. They compete on speed, but they all follow ECMAScript. So your code behaves the same on all of them. The differences are performance, not behavior. They also compete on how quickly they adopt new language features. Which is why some features land in one browser before another. The specification arrives first, the implementations follow. Let us recap the whole path. Source text goes into the parser. The parser produces tokens, and the tokens produce a tree. The tree becomes bytecode, which starts running immediately. Hot functions get compiled to machine code by the JIT. And unstable types can undo that work. That is how JavaScript actually runs.